All right, let's jump right in today. We're going to be exploring this fascinating world of quantum autoencoders.
Oh, yeah. It's
a cool topic for sure.
Yeah, we're basing this deep dive on an essay by Jorgo Schneeppert. And, he really goes into how these systems could reshape the way we think about handling these just massive data sets that are emerging from, quantum chemistry, material science, you name it.
Yeah, and I mean, that's one of the big things here, right? Is we generate so much data now from all these different, scientific fields that it's hard to even know where to begin to make sense of it.
Right.
And that's what's really interesting about quantum autoencoders is they offer this potential to go beyond just, simply shrinking file sizes.
Right.
Yeah, like you might, zip a file on your computer.
Yeah.
It's operating on a whole other level, leveraging the strangeness of quantum mechanics to actually find and isolate the core essence of that quantum data. So it's not just like blindly, squeezing the data down. It's more like finding the hidden blueprint, the essence of what's going on.
Exactly. It's it's like finding the signal within the noise.
Yeah, that's a great way to put it.
Yeah.
But before we get too deep into that, let's maybe rewind a bit.
Sure.
For anyone who maybe needs a refresher on, how would you explain the core advantage that quantum computing has over the classical computers we use every day?
Yeah. So it really boils down to qubits.
Okay.
And unlike a classical bit, which can be a 0 or a 1, a qubit can be both simultaneously thanks to superposition. So think of it like a coin spinning in the air before it lands. It's in this uncertain state of heads and tails until you force it to choose. And so that's the power of a qubit. It can hold this,
So it's not just two options. It can hold like a whole spectrum.
Right. It's a spectrum of possibilities.
Okay. I see how that could lead to these massive leaps in processing power.
Exactly.
But what about entanglement?
Right.
Schneeppert mentions it as being key to quantum autoencoders too. How does that fit in?
Yeah. Entanglement is where things get really mind-bending. It's this idea that two linked qubits, no matter how far apart, can influence each other instantly.
Okay.
So imagine two of those spinning coins, right, like light years away, and they suddenly land on the same side at the exact same moment.
That's wild.
That's the kind of interconnectedness that you get with entanglement.
Right.
And it allows quantum computers to solve certain problems exponentially faster.
Wow. That's a lot to wrap your head around.
It is. It is.
So how do autoencoders, something we use in classical computing, fit into this quantum picture? How do those two things come together?
Yeah, so in classical computing, autoencoders are like really clever packing algorithms.
Okay.
Right? You have an encoder that compresses a large file down to a smaller size, and then a decoder that reconstructs the original when you need it.
Okay.
And the trick is that the encoder learns to extract only the most essential information.
So they're not just randomly deleting data.
Right.
They're finding the important parts.
Exactly. They're finding the patterns, the core features that represent that data.
Gotcha. So does that same idea then apply to quantum autoencoders?
Yes, absolutely. So quantum autoencoders take this idea and they apply it to the world of quantum states and transformations. So they're still looking for the essence of the data, but now they're doing it within the rules of quantum mechanics.
So we're taking the weirdness of quantum mechanics and using it to build like a better compression system.
Exactly. And that's what gives us this incredible advantage.
Okay, well, what kind of advantage does that give us? But what's the benefit there?
So the biggest one is efficiency. Quantum autoencoders can process quantum data directly without having to translate it into the classical bits that our everyday computers use.
Right.
And that makes them incredibly efficient at handling these incredibly complex data sets coming out of things like, quantum chemistry simulations.
Gotcha. So they're purpose-built for this quantum world, which makes sense.
Exactly.
Schneeppert's essay highlights some really interesting potential applications. So let's dive into those.
Sure.
First up, quantum communication. How could quantum autoencoders change the way we send data in the future?
Yeah, so imagine a quantum internet, right, where information travels via entangled qubits.
Okay.
Quantum autoencoders could make this communication faster and more efficient.
Oh, wow.
By compressing those quantum states before they're sent.
Okay.
It would be like sending a high-definition video but compressed down to a tiny file size.
That makes a lot of sense. Faster communication is always a good thing.
Exactly.
But what about security?
Yeah.
With all the concerns around cyber attacks and data breaches, how could quantum autoencoders play a role in protecting our information?
This is where they really shine. Quantum autoencoders offer a really powerful tool for quantum cryptography.
Okay.
So imagine using them to secure quantum keys, which are essentially strings of entangled qubits used for encryption.
Mm-hmm.
By compressing these keys, we can make them easier to store and manage without sacrificing security.
So it's like an unbreakable code that's also incredibly efficient.
Exactly. Yeah, it's like having your cake and eating it too.
Yeah, I like that. That's a great analogy.
Yeah.
But let's move on to the next big application.
Sure.
Quantum machine learning. How could compressing data actually improve the performance of these algorithms?
Yeah. So think of quantum autoencoders as the ultimate data chefs for quantum machine learning.
Okay.
They can take this complex quantum data and they can simplify it before feeding it to these classical machine learning algorithms.
So it's like they're prepping the ingredients to perfection.
Exactly. Yeah. They're extracting the most relevant features, which leads to faster training and more accurate results.
I'm seeing how versatile these quantum autoencoders can be.
Yeah.
But Schnephat also acknowledges that there are challenges and limitations on the horizon.
Right.
What are some of the things that are maybe holding us back from widespread use of this technology?
Well, one of the biggest hurdles is decoherence. And this is that fragility of qubits that we talked about earlier.
Right.
They're extremely sensitive to their surroundings, and their quantum properties can easily be disrupted, which leads to errors in computation.
Okay, so it's like trying to build a sandcastle on a windy beach.
Exactly. It's a very delicate process.
Okay, so we need to find ways to make these qubits more robust.
Right.
What else is standing in the way?
Another challenge is interpreting those compressed quantum states. You know, even though we can describe the compression mathematically, actually understanding what those compressed states represent can be very tricky. It's like having a dictionary with no words. Just abstract symbols.
So we need a quantum Rosetta Stone to really unlock the full potential.
Exactly. We need new tools and techniques to help us decode that information.
That's fascinating.
Yeah, and on top of that, building these quantum autoencoders requires a blend of expertise from physics, computer science engineering. You know, bringing all those disciplines together is a challenge in itself.
Yeah, it sounds like we're on the frontier of a whole new scientific paradigm, which always comes with its own set of challenges.
Absolutely.
But it also sounds incredibly exciting.
It is. It's a very exciting time to be working in this field.
Well, folks, that wraps up the first part of our deep dive.
Yeah.
We've unpacked the basics of quantum computing and how those principles can be leveraged to create these incredible compression systems.
Yeah, we've laid the groundwork.
Exactly. And in the next part, we'll dive deeper into the technical intricacies of how these quantum autoencoders actually work.
Yeah, we'll get into the nuts and bolts.
Exactly. We'll explore the algorithms, the hardware needed to bring them to life.
It's going to get fun.
It is so. Until then, keep those quantum minds buzzing. We'll see you back here for the next part of our deep dive into quantum autoencoders.
See you then. Welcome back to our deep dive into quantum autoencoders. In this part, but we're going to kind of shift gears a bit and really get into the nitty-gritty of how these systems actually work.
Yeah, you're right. Things are about to get a little more technical, but stick with us. We'll guide you through it.
Absolutely.
So where do we start this technical journey?
So let's start with the mathematical foundations. You know, quantum autoencoders rely heavily on two key concepts: density operators and unitary transformations.
Okay, that sounds pretty abstract. Can you give me like an analogy to help me grasp what a density operator is?
Sure. So imagine a weather forecast that gives you the probability of rain, you know, let's say the 70% chance.
Okay.
The density operator is kind of like that forecast, but for quantum systems, it captures the uncertainty inherent in these systems. You know, it tells us the likelihood of finding the system in various states.
So it's not giving us a definite answer, but like a range of possibilities.
Yeah, exactly. It's a probabilistic description.
Okay, what about those unitary transformations? What role do they play?
So unitary transformations are essentially operations that change a quantum state into another state, but in a way that preserves its quantumness. It's kind of like rotating or reflecting an object in space, but instead of a physical object, we're manipulating these quantum states.
So we're transforming these quantum states without destroying their delicate quantum properties.
Right, exactly.
How does that tie into this idea of compression?
Yeah, so the magic happens when we apply a carefully crafted unitary transformation to a quantum state.
Okay.
This transformation is designed to essentially squeeze the information down isolate the essential parts, and discard any redundancies.
So it's like a quantum sculptor chiseling away the extraneous bits to reveal the essence of the information.
That's a great way to visualize it, yeah.
And this whole process, this is all happening within the realm of quantum mechanics. Leveraging these principles of superposition and entanglement that we talked about earlier.
Exactly.
Okay, we briefly touched on this idea of a loss function earlier.
Right.
When we were talking about classical autoencoders.
Yeah.
Does that same concept apply in the quantum world?
Absolutely. The loss function in a quantum autoencoder measures how well the reconstructed state matches the original after we've compressed it.
Okay.
So essentially it tells us how much information was lost during the compression process.
So it's a way to gauge the fidelity of the compression.
Exactly how faithful is that compressed version to the original.
Right. And here's where quantum mechanics offers a unique advantage. Right? Unlike classical autoencoders, which rely on approximations, quantum autoencoders can quantify that compression with incredible precision.
Exactly. We can directly measure the reduction in the number of qubits needed to represent that compressed state.
Okay. So we've laid down the mathematical groundwork.
Right.
But how do we actually build these quantum autoencoders? What kind of hardware and software are we talking about?
Yeah, so that's where the world of quantum computers and programming frameworks comes in. You know, quantum autoencoders need sophisticated hardware capable of performing these complex unitary transformations on qubits.
So we need those stable error-corrected qubits.
Exactly. We need universal quantum gates. We need robust error correction mechanisms.
So we're talking about platforms like IBM Quantum or Google Sycamore.
Yeah.
The ones we hear about in the news.
Exactly. Those are prime examples of the kind of hardware we need to really explore and implement these quantum autoencoders.
And what about the software side of things? What tools are quantum programmers using to actually build these algorithms?
Yeah, so there's a whole ecosystem of software frameworks emerging.
Okay.
You know, you have Qiskit, which is an open source library from IBM that lets you design and execute quantum circuits.
Okay.
You have TensorFlow Quantum, which extends the popular TensorFlow library to work with quantum data. And then you have PennyLane, which is another powerful framework for doing these hybrid quantum classical computations.
So these frameworks provide the building blocks and like the programming language for quantum developers.
Exactly. They give developers the tools to translate our mathematical understanding into algorithms that can run on these quantum computers.
We talked earlier about how quantum autoencoders offer some significant advantages over their classical counterparts. Can you remind me what makes them so special?
Yeah, so one of the biggest advantages is their efficiency in handling these complex data sets, particularly those coming from quantum simulations.
Right.
You know, as the systems we're simulating get larger, the computational demands grow exponentially for classical computers.
Right.
Quantum autoencoders, however, can process this quantum information directly, making them much more efficient for these kinds of problems.
So they're built specifically for the quantum world.
Exactly.
Okay, is there anything else that sets them apart?
Another key advantage is the precision with which they can quantify data compression. You know, we can directly measure the reduction in the number of qubits, giving us a very clear metric for how effective that compression process is.
Okay, I'm getting a much clearer picture now of how these quantum autoencoders work and the potential they hold.
Yeah.
In the first part, we touched on some of those exciting applications.
Right.
Can we dive a little deeper into those? Starting with quantum communication?
Sure. So imagine a future where we have a quantum internet, where data is transmitted through these entangled qubits.
Yeah.
Quantum autoencoders could make this communication faster and more efficient.
Oh, wow.
By compressing those quantum states before they're sent.
Okay.
Think of it like sending a high-definition video, but compressed down to a tiny file size.
Right, but with the added security of quantum entanglement.
Exactly. It's the best of both worlds.
That's a pretty compelling vision. What about the role of quantum autoencoders in cryptography?
Yeah, so they're a perfect fit for securing quantum keys.
Okay.
These keys, which are made up of entangled qubits, are incredibly secure, but they're also complex to manage. Quantum autoencoders allow us to compress these keys, making them more manageable without sacrificing that security.
So it's like creating an unbreakable code, but it's also efficient to use.
Exactly.
So quantum autoencoders could lead to a future where our data is both highly secure and efficiently transmitted.
Absolutely. That's the goal.
That's pretty remarkable. What about the application in quantum machine learning?
How
do they improve these powerful algorithms?
So think of them as intelligent data preprocessors for quantum machine learning. They can simplify that complex quantum data before it's fed into those classical machine learning algorithms. This preprocessing helps extract the most relevant features, leading to faster training and more accurate results.
So they're like expert chefs prepping those quantum ingredients perfectly.
Exactly, yeah. They're making sure that the data is in the optimal format.
It seems like quantum autoencoders could be the key to unlocking the true potential of quantum machine learning.
I think so too.
But we can't ignore the challenges. Earlier, we mentioned the issue of decoherence. Can you explain that a little more?
Yeah, so decoherence is one of the biggest hurdles we face in quantum computing. It's this tendency of qubits to lose their delicate quantum properties due to interactions with their environment. It's like trying to build a sandcastle on a windy beach. The slightest disturbance can cause it to crumble.
So to make these quantum autoencoders more reliable, we need more robust qubits that are less susceptible to this decoherence.
Exactly. We need to find ways to shield them from that noise.
Okay. What other challenges do we need to address?
Another big challenge is interpreting those compressed quantum states. You know, we can describe the compression mathematically, but actually understanding what those compressed states represent is a whole other ballgame. We need new tools and techniques to help us decipher those compressed messages.
It sounds like we're still in the early stages of unlocking the full potential of these quantum autoencoders.
Oh, absolutely. We've only just begun to scratch the surface.
There's a lot more work to be done.
A lot more work to be done, but it's exciting work.
It certainly sounds like it.
Yeah.
Welcome back to the final part of our deep dive into quantum autoencoders. You know, we've explored the science behind them, the potential applications. We've even gotten into the technical weeds a bit.
Yeah, we've covered a lot of ground.
But as we wrap up, I think it's crucial to kind of take a step back and look at the bigger picture. You know, what are the long-term implications of this technology? Where do we go from here?
That's a great point. You know, it's easy to get caught up in the excitement of new discoveries, but it's important to consider the potential impact, you know, on society as a whole.
Exactly. One area that comes to mind is the impact on different industries. You know, we've talked about quantum communication, cryptography, machine learning. Where else could quantum autoencoders make a real difference?
Yeah, well, I think the possibilities are vast. You know, one area that Schneppat touches on in his essay is material science. You know, imagine being able to simulate these complex molecules efficiently by compressing their quantum states. This could revolutionize how we design new materials. Leading to breakthroughs in everything from energy storage to drug discovery.
So we could design materials with specific properties, you know, tailored to our needs just by using these quantum simulations.
Exactly. It's like having a molecular toolbox where you can pick and choose the properties you want.
That sounds incredible. It's like something straight out of science fiction.
It does, doesn't it? But that's the power of quantum computing. It allows us to explore the world at a level of detail that was previously unimaginable.
I'm starting to see how these quantum autoencoders are more than just a, you know, cool technical feat. It's like a gateway to a whole new way of understanding the world around us.
Absolutely. I think that's a great way to put it.
But, you know, alongside all this excitement, there are also some big questions we need to be asking, right? What are some of the challenges, the potential pitfalls that we need to be aware of as this technology develops?
Yeah. One of the key challenges, I think, is making sure that quantum autoencoders are developed and used responsibly. You know, we need to think carefully about the ethical implications, particularly around privacy and security.
Yeah, if we can compress sensitive information so efficiently, we need to make sure that doesn't fall into the wrong hands.
Exactly. It's a double-edged sword, right? We have this incredibly powerful tool, but we need to figure out how to use it safely and ethically.
So what are some steps we can take to ensure that happens?
Well, I think we need to establish clear guidelines and regulations around the development and deployment of quantum autoencoders. This will require collaboration between scientists, policymakers, industry leaders.
A multi-pronged approach.
Exactly. And we also need to educate the public about the potential benefits and risks of this technology.
So it's not just about, you know, advancing the technology itself. It's about building a framework around it to make sure it's used for good.
Absolutely. It's about shaping the future of this technology in a responsible way.
What are some specific areas where we need to be particularly cautious?
Well, one area is the potential for bias in quantum algorithms. You know, just like classical algorithms can inherit biases from the data they're trained on, quantum algorithms are also susceptible to this.
Right. We don't want to replicate or even amplify existing biases just because we're using this new type of technology.
Exactly. We need to be very mindful of this and develop techniques to mitigate bias in these systems.
And another thing that comes to mind is accessibility, right? We need to make sure that the benefits of quantum computing, including quantum autoencoders, are accessible to everyone, not just a select few.
Absolutely. I couldn't agree more. You know, it's like with any transformative technology, we need to make sure it benefits all of humanity.
So what can we do to promote that kind of equitable access?
Well, I think we need to invest in education and training programs that make quantum computing accessible to people from diverse backgrounds. We also need to create opportunities for collaboration and knowledge sharing across different communities and countries.
It sounds like we need a global effort to make sure this quantum revolution really benefits everyone.
I think so too.
Okay, so let's shift gears a bit and talk about the future.
Yeah.
What are some exciting research directions that you're keeping an eye on in the world of quantum autoencoders?
One area that I'm particularly excited about is the development of these hybrid quantum classical systems. You know, these systems combine the best of both worlds. They leverage the power of quantum computers for specific tasks while relying on classical computers for others.
So it's not about replacing classical computing entirely, but finding ways for the two to work together.
Exactly. It's about finding the right balance, finding the synergy between the two.
And within that realm, researchers are exploring how to optimize the interaction between those quantum and classical components.
Right.
Which is really crucial for the efficient training and deployment of these quantum autoencoders.
Absolutely. It's all about making those systems work together seamlessly.
Okay, so we're looking at ways to improve that interaction. What other areas are researchers focused on?
Another exciting area is the development of new quantum algorithms specifically tailored for these autoencoding tasks.
Okay.
You know, as our understanding of quantum computing grows, we're discovering new ways to manipulate quantum information, leading to more efficient and powerful algorithms.
So it's not just about applying existing quantum algorithms to this new problem.
Right.
It's about creating algorithms specifically designed for quantum autoencoders.
Exactly. It's about pushing the boundaries of what's possible.
And this research isn't happening in isolation, right? There's a growing emphasis on collaboration.
Absolutely.
Between theoretical and experimental researchers.
Yeah, that synergy is crucial for making real progress.
It sounds like a truly interdisciplinary effort.
Yeah.
You know, bringing together these brilliant minds from different fields to tackle this really exciting challenge.
It is. It's a very collaborative field.
Well, folks, that brings us to the end of our deep dive into the world of quantum autoencoders. We've covered a lot of ground, from those fundamental principles to those potential applications and the challenges ahead.
It's been a great discussion.
It has, and a big thank you to Yorgo Schneepat for his insightful essay that really sparked this fascinating conversation.
Yeah, his work is really groundbreaking.
It is, and I hope this deep dive has given all of you listening a glimpse into the transformative potential of these quantum autoencoders.
I hope so too.
You know, this technology has the potential to revolutionize countless industries and fundamentally change how we interact with the world around us.
It's a very exciting time to be following this field.
It is. And as we move forward, it's crucial to remember that this technology is in our hands. You know, it's up to us to shape its development and ensure that it's used to benefit humanity.
Absolutely. We have a responsibility to use this technology wisely.
We do. And with that thought-provoking note, I think it's time to wrap things up. So until next time, keep exploring, keep learning, and keep those quantum minds engaged. Thanks for joining us.
Thanks, everyone.